Hello, I'm Srujan and this is group 3 and my teammates are Charles Gani, Lalit Sarab Golapuri and Shreya Reddy Dubaka. So today we'll be learning about unlocking images, which is basically content-based search using color histogram framework. So as you know, nowadays billions of images are being uploaded in the internet every day, and it has been difficult to track down and search every image based on the visual appearance. So to deal with this problem, we use CBIR, which is content-based image recognition, or we can track down features like color or the histogram counts or textures and other related specific features which are hidden in the image to track down and respective image. As we see here, the agenda for today is we'll talk about image search problem, the conventional versus content-based methods, and also we'll talk about a little bit of histogram framework too, and I'll talk about the workflow and the pipeline and all the technical details that we have done to implement this framework. I'll show you my results which have gotten after executing the MATLAB functions, and also what improvements can be done and what are the gaps in between my framework and the framework which is robust and more accurate. So without any delay, let's go to the next slide. So let's talk about some basic introduction. So what is CBIR? As I said, CBIR is content-based image retrieval. So it searches a specific feature in an image and tracks down based on a certain feature or certain quality of the image. So as we know, we can use CBIR use similarity measurement, which is basically the similarity between the particular image and the desired image. We can use cosine similarity, Euclidean similarity, Manhattan similarity to calculate the similarity measurements, and this is one of the core features. So why does this actually matter? Why does CBIR actually matter? So as I said, billions of images are being uploaded daily, and text search is not enough to actually get visual similarity matters. And where do we actually use this? We use this in X-rays, medicines, and also in security cameras. To find the culprit, we can use CBIR method to actually track down a culprit using the features. So let's go to the next slide. How image search usually works. So how does this actually work? So usually in the image search can be based on few tags which are file names, and also the metadata, the data which is inbuilt in those images. And what are the strengths in this? So text matches, and this is very simple. You can easily find out and figure out a image using the file name and also the metadata. But as you know, the results are actually poor and the accuracy is very less. And on a large scale, if we used text matches or simple tags or the basic color metadata, it gets harder to actually retrieve an image, because we're scaling on millions and billions of data every day. What are the strengths and limitations? So the strengths are CBIR is very fast, it scales well, and it doesn't need any labels, and it also works very well for all the color dominated images. Color is not at all an obligation here. But what are the limitations? Let's talk about the limitations. It ignores the pattern of those images, like it ignores the shape. A color pattern with a triangle and a color pattern with a square, if it has equal number of pixels and his counts, both will show the same result, due to which we might get some false matches with the same colors but the different object shape. As we talked, there is no semantic or contextual understanding. So let's talk about the literature review here. So what is a color histogram? So color histogram is the pixel intensity values of an image. So here each bin shows each intensity, and we use this to retrieve the similar images in our CBIR framework. Why do we use this? Because this is fast, effective, and it compresses complex images without actually increasing the computational time. And what are the implementation framework which we have used here? So we generally take an 8-bit image and we convert it to a 6-bit image. So we're basically converting it from 256 bins to 64 bins. We take first two MSG, which is most significant bits from each channel, which is R, G, and B, and we combine them together to get 2 into 3, which is 6-bit. And we then calculate hist counts. Then we calculate the distances between each image, which is similarities in our database. And then we sort top 20 images which are close to each other. And then we use our CBIR framework to retrieve the image. So the technical pipeline is more detailed in this page as compared to the last one. So we collect untagged images, we convert them into a 6-bit color space. Then we use hist counts to extract the exact color histograms. And as I said, this is a 6-bit integer, 6-bit, hence it has 64 bins. And then we process query image the same way. Then we measure the distances between each of them, which is measure of similarity. So in our project, we used Euclidean distance, which is square root of difference between two images whole square, which I'll be talking in the next slide too. And then we rank them and display the top matches. So as I said, the use cases here are this is like very much used in medical labs, medical data, to identify similar scans, to identify similar cases in different diagnosis of work. And also this is majorly used in security, which is basically a CCTV match search. So instead of searching CCTV footage by date and time, we can use specific features like car or a number plate or any hidden details which are there in the image, which is like very important use case in day-to-day life. And also we use this for searching art, research, and whatnot. So the results which I've gotten from my framework are these. So this is the image I got for the pick 101. This is the image I got for the pick 54, 21, and 1, and this one is the remaining pick. So the results and analysis. Let's talk about some analytical stuff here. So the precision is basically the value of relevant retrieved images by total number of images retrieved. So as you can see here in the image, the total number of images retrieved are 20, and the similar images here are 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 by 20 goes here, which is 0.45. And the recall here is relevant images by total number of relevant images in the database, which is 5 by 5, and that's 1, which we got. So let's talk about some improvements and insights which we can learn from here. So we used Euclidean distance to calculate the similarity, but to enhance the accuracies, as we got the precision as 0.45, to enhance the accuracies we can use cosine distance similarity to get better result. And also we can use hybrid features which include spatial and semantic description of an image, which eliminates the whole problem of spatial arrangement in histograms, color histograms. And also we can use reinforcement learning, which is the next step. We can induce many machine learning algorithms to comprehend the data and summarize the data. We can use many land graph models, LLMs too in future. So in conclusion, everything, this method is very fast. It gives the data so quick because it calculates the color histograms too soon because it's a 6-bit integer, 6-bit data. But what does it miss? It misses texture, shape, and spatial info, which is very important to get the better accuracy of retrieval. So, and it can't do semantic or object level understanding way too good. So what are the solutions here? We can add special features here called as texture and shape descriptors, and we can use pre-trained neural networks and machine learning algorithms for better understanding and better data flow, which gives a good output as our machine learning algorithms try to understand what are the patterns going on there, and it gives the better result as we reinforce them by giving proper testing and training data. So we talked about the real world examples, and also now these are the references which I referred to. Now let's go to the demo. So this is our code. So first we'll go to RGB to 6-bit code. So basically here I'm taking input as an untagged image, and I'm converting the image into 6-bit from 8-bit by taking 2 of the most significant bits of each channel and combining them together. Then we go to get hist counts, where we calculate color histograms for each image, as you can see here, and then we calculate the distances. As you can see here, this is the Euclidean distance which we have used, and we can also use cosine similarity, as I told, which is more robust. And then we rank the data here, and then we implement our CBIR framework. So I'll be running this here. You can see a box where we can select the image which we need. So I'm selecting 101. So this is the result we get. So these are the similar images for the query 101. As you can see, we got n number of images which are almost similar, but some things are different. So what do we infer from this? So basically the spatial pattern is different in these, but if we talk about only the color, which is green, yeah, these all colors actually make sense. But when we talk about the spatial arrangement or the shapes, these bottom 2 rows are not similar, but based on the color they're similar. So yeah, this is it for now. Hope you had some good explanation. So, and also there's one more thing I wanted to show here. Let's take one more picture to actually analyze what's happening here. Let's select image 138. Okay, so what do we get here? So image 138 has 1, 2, 3, 4, 5, 6 similar images, but they're not perfectly the same, but 6 similar images. And out of 20, all other images are different. As you can observe, all these images have the color pattern as their whole similarity. You can see red, blue, and purple, which is the same almost in all the photos. So as I told you before, color histogram method, 6-bit color histogram method, basically deals perfectly with the color distribution rather than the spatial arrangement. But this is very quick to retrieve the images, and it's one of the basic but fastest method to get the proper retrieval using CBIR framework. and